All right, thanks everyone. So first I want to say that despite my title here, I do not want to dwarf any of the other presentations. You can thank Connor for that one, but in all seriousness, the title of my presentation is Investigating Hyperinflated M-Dwarfs in Eclipsing Binary Systems. And so I am going to, in this presentation, take you through that jargon-filled title, starting from the end of it, going backwards, and defining all of those terms. And so a few things about this project. It was a senior thesis in the astronomy department, and I was working with Professor Phil Muirhead, who's a professor there. And yes, so let's go on to the first step, the first slide, going into eclipsing binary systems. So you'll see this title keep coming up here with different parts highlighted. So what are eclipsing binary systems? So this movie explains it better than any text could. So you see here there are two stars, and the stars are orbiting around each other. Each time one star passes in front of the other from our line of sight, that thing on the bottom there, which is brightness plotted against time, that's called a light curve, will have a dip in it. And so as it keeps playing here, you'll see that one star passes and the light coming from the system decreases. And so this happens every time we have an eclipse of one of the stars. And so my project is looking at two eclipsing binary systems, so 4 stars in total. And these systems are really special because they allow us to learn about the properties of each individual star without knowing a whole bunch about the system in general, including a very important quantity, which is distance. Distances are hard to get usually. We don't need to know it to learn about the stars in eclipsing binaries. There we go. So next step in the title, what are M-dwarfs? What are these? These are stars. And so what we have here is a very famous plot of most of the stars you'll see in the galaxy. You can think of it as kind of a field guide to the stars in our galaxy. And so the axes here are temperature, surface temperature of the star on the bottom, and then luminosity, which is, you can think of just as power. It can be measured in watts on the y-axis. And the most important thing here is to realize that temperature is increasing to the left here, not to the right. And so blue is hotter, red is cooler. That throws a lot of people, including myself in 200 level astronomy, for a loop. And so you see that the hottest, most luminous stars are up here on this diagonal part called the main sequence. But then down here, we have those redder, cooler, and smaller stars. And that's where we're focusing on M-dwarfs. That box indicates the rough region where M-dwarfs are on this field guide. And so that leads to the question, why M-dwarfs? Why are we interested? We have these big, bright, luminous stars. Well, why are we interested in these tinier, dimmer, fainter, smaller stars in the sun? So there are a few reasons. The first is that they make up the majority of stars you'll find in the galaxy. So 70%, and more than 70% of all stars are M-dwarfs, in fact. Despite this, they're tough to see. You could look up in the night sky tonight, even if not even here in Boston, go out to Maine or something where it's really dark, and you will not see a single M-dwarf with your eye in the sky because they're dark enough, dim enough, that you need a telescope to have any chance of seeing them. So because of this, we don't know a whole bunch about them. Those big bright ones we can look at with pretty small telescopes, get a lot of information. These small ones, that's tougher. So finally, they are friendlier to potential life. And so that means that we've found now thousands of planets around other stars. And the problem with planets around those big massive stars is that the big ones emit a whole bunch of radiation. They also have a bad tendency to explode about 100,000 years into their lifespan, which sounds like a lot, but for life developing, it's like that. These stars live a very long time, and they do not emit as much of that dangerous radiation. And so here on the right here is an artist's conception of a planet we found around the nearest star to our sun, which happens to be an M-dwarf. There's the star, and this is called Proxima Centauri b. So finally, hyperinflated. What is this jargon here? And so I'm going to use a picture to illustrate this. Here's the sun, and so the sun, everything else is going to be scaled to this circle. Here's what we expect the two M-dwarfs that we're considering. Each one of these is in its own eclipsing binary system. This is the size we expect them to be. And then here's what is published currently. And so back in junior year, I was doing a UROP-funded project, just basically bookkeeping, trying to make a whole list of M-dwarfs in eclipsing binary systems that we knew about. And these both really stood out because they're much bigger than we think they should be. And so I wanted to explore whether that was a physical reality or maybe something went wrong in the data process, the data analysis. So now the investigation part of the title. So the first step I did in this investigation was running models because, like I said, there are physical possibilities that could fit what these publications are saying, what those big sizes were saying. And so these models were the first step so that I could get some kind of intuition into whether there was even a possibility of a physical reality for these stars. And then so the second step was analyzing new data. This really, you have to do this no matter what, because without the data analysis is where they get all the numbers from in the publications. So we did our own with as much independent data as possible to try to compare what we got to the published results. And so there were two steps to this. When you have eclipsing binaries, you need two types of data. The first kind is the light curve that you saw in that first slide with the movie. The light curve, light as a function of time, brightness as a function of time. And for that, I accessed an archive of data. So I didn't actually take the data for this, but I found it on an archive for free. And so this is called the Wide Angle Search for Planets, or WASP. And it's basically an array of a whole bunch of souped up cameras that are good at staring at points in space over a very wide angle for long periods of time. Perfect for finding light curves, brightness as a function of time. Second was a little bit of proprietary data. So this is a picture of the outside. It's a little dark because I took this at sunrise when I went out there and visited. It's the Discovery Channel telescope out in northern Arizona, about an hour out of Flagstaff, hour and a half if there's snow like there was in January for me. And so you also need spectroscopic data for eclipsing binaries. And basically what that means is that you can't just be looking at the light. You also need to see how the stars are moving as a function of time. And so from a spectrum that we got from here with a very, very high-powered instrument, we're able to get to, as the stars move, they change the speed along the line of sight. So when they're moving directly towards and away from us, the velocities are maximum. And when they're moving perpendicular to our line of sight, the so-called radial velocity is 0. So that was the other kind of data we analyzed. And then finally, we compared these results. So first off, those models. They suggest that the stars formed millions of years apart, which is unlikely for the hypothesis that there's actually a physical reality to these inflated sizes, because if they were that big, they would be young, because stars start as these very big clouds that slowly, or actually, depending on your time frame, slowly or very quickly collapse down into the stars they are on the main sequence. And so the models here's one example. This is a plot of the star age on the bottom here, logarithmic, versus the star radius, also logarithmic. And so older is to the right, and bigger is up. And so the red and the blue are the two components of one of these two eclipsing binary systems. So each line there, each solid line is a star. And then, so the model is those tracks going downward. And so you can see they're getting smaller as they get older, as we expect. But if they both formed at the same time, the lines of their current radii, as published, would intersect at roughly the same time point. But you can see that red here intersects at 10 to the 7th, and then blue intersects at 3 times, or about 30 million years. So there's tens of millions of years between the supposed formation times of these stars. That can't happen, and so this casts some doubt onto the physical reality of these systems being hyperinflated. So then the second part, the data analysis. Here's a light curve, again, from that movie. It's the same thing. It's the brightness as a function of time for both the primary and the secondary eclipses, along with a model that we fit to the data in red. And then the residuals are down at the bottom here. And so you can see that we got a decent fit to both of these. And so that means that as we tweak the parameters of we had another model that we were turning some knobs to get some fits. When you get a good fit, you stop turning the knobs and you read off, not literally turning knobs, but metaphorically, you read off what the value is, and those are your masses and radii for the stars. Then, like I mentioned, there's this other part to the data, which is the radial velocities. And so, as I mentioned, they're 0 at the points where they're going perfectly perpendicular to our line of sight. And the key thing to notice here is that the amplitudes are different in the published values. This is the published values that led to the hyperinflation results. The amplitudes are different. The difference vertically between this lower point and the top point here are different than these two. But our new Discovery Channel telescope radial velocities, although it's only 2 data points, they suggested a much more symmetric radial velocity result, which would imply equal masses and also would change the total length scale of the problem. So instead of using more words, I'll just show the pictures again to wrap it up. So the new data analysis shows that there's no hyperinflation at all. So this is just nothing changed from before. But when we have those new radial velocities, it changes the expected size of the stars So that one, we expect it now to be much more large. So then our new result corresponds to what we expect, but the stars are no longer hyperinflated because the expectation is in line with what we actually get. And so there's the references that I used for this presentation. There's many more in the actual senior thesis. And now I'll take any questions. Yes, Professor
One of the
Campbell.
most exciting things are these exoplanets around. Can you say a little bit more about that for the audience?
Yes, and so we're excited about exoplanets because the big question that I think most humans are interested in knowing one way or another is there life out there besides us? You know, it's a driving question of when NASA comes up with their policy for making exoplanets a big part of it. They always say the end goal is to possibly find life in the galaxy and the universe besides us. Now, so with recent technology, we've discovered thousands of planets orbiting other stars and confirmed them, but you really need to know the star to know the planet. And so if we want to find life, at least as we know it, we need to find planets that are hospitable or habitable for that life. And so M-dwarfs being cool, and like I mentioned, they live very long. In fact, an M-dwarf has not, and no M-dwarf that has come into existence yet has died or gone through its cycle naturally. There could be exceptions, but their lifespans are expected to be longer than the age of the universe. So it's very important to know about the stars because, like I also mentioned, those very massive, big ones, they blow up really quick, and you will not be getting much life. There will be not a lot of time for life to form, if it forms at all. And so M-dwarfs are one of the places that scientists are looking for not only planets, but habitable planets. Yes?
So I really enjoyed your talk. I wonder, does your work suggest that there are a lot of pairs out there that now need to be reevaluated?
Yes, it does. I was working very closely with one of the graduate students in Professor Muirhead's group, and she is still working on a paper, but she has a result that is similar to mine. The same research group, in fact, has published several of these eclipsing binary systems with hyperinflated M-dwarf stars in them. And so, yes, we're trying to get a relationship between the mass and the radius of these low-mass stars. So it's very tough when you have a nice line, and then you have these stars that are way above the line because they're so big, according to the publication. So yes, there could be more systems like this where I think the key was our radial velocities, using that Discovery Channel telescope, and the instrument attached to it was the key.
Have you reached out to that group to figure out, like, there could be many reasons why that's happening? Could be faulty data.
Yeah, I have not reached out personally. I don't know when this graduate student publishes, she will hopefully probably get in touch with them somehow. But it's you can talk all day about, well, should you get in touch before you even publish? But I think at some point we will, and try to figure out what's going on, because it is very important for learning more about these stars, which in turn leads to very exciting things like planets and life. Thank you.